here. It's been great so far. So I want to talk about two topics in a gentle, relaxing, not detail-oriented, touchy-feely way. And the first one is the Gage-Nastrom spectrum, and Ted Shepard commented on that a couple of times about the atmospheric energy spectrum and the observations and the possible explanations for it. So that will connect to that part of the talk, part of the lectures. And the second, and the work on this was done with Jörn Kallis and Raffaele Ferrari, and that work is more or less complete. And then the second topic, which is kind of mystifyingly in this title here, is recent work that's still ongoing, and it's about to be submitted with Jim Thomas, who's a PhD student in New York, and Schaefer Smith, who's a colleague there. So to start at the beginning, this is the plot that Ted already showed. So this is the Gage-Nastrom data, the original data collected in the 70s on commercial airliners flying across the Atlantic. And basically these were instrumented such that they could measure the two horizontal velocity component and also buoyancy along those flight tracks. And because they were flying back and forth a lot, they collected very high quality data. And when this data was then prepared for publication in these two publications by Nastrom and Gage and Nastrom, this is the plot that everyone took away from that. So just to talk you through that again, this is really wave number along the flight track, or here written as wavelength. And these are these power spectra of the zonal wind, the U component, the meridional wind, V, and the potential temperature. Now the first thing you need to notice is that these have been spaced apart by a decade just for clarity. They're all on the same scale, so they all more or less have the same spectrum. And what they have is a steep k to the -3 looking spectrum at the larger scales that then perceptively shallows and maybe follows a k to the -5/3 after a kind of transition zone, which is more or less in the region of a few hundred kilometers, something like 500 to 700 kilometers wavelengths. And as Ted described, no one is particularly surprised about the k to the -3 at the large scales, it being the kind of typical wave number scaling you would expect for an entropy cascade going downscale. But the k to the -5/3 at the smaller scales is kind of open to speculation. What causes that part of the spectrum? And the reason it's open to speculation is, as Ted also said, is there's a large number of processes that all, the simple theory, they will all give you that power law. So so the first message really is that it's not much point thinking too much about individual power law slopes if we don't understand what the process is. So understanding the spectrum and its implications has been going on ever since. This experiment was repeated in the 90s, the Mosaic campaign, but more or less the same outcome, but it's a larger data set and more readily available. Okay, so going back to the beginning, which will come to no surprise now, you have all know this, but the first question, of course, is why isn't it just that whole spectrum not just all turbulent? Why isn't it all k to the -5/3? So this is repeating something you all know. But if you just looked at the Reynolds number in the atmosphere, say, with kind of typical wind speeds and typical length scales and typical values for the viscosity, it would be phenomenally large. And in the ocean, it would, even though the speeds are so much smaller and the lengths are so much smaller, the viscosity is also smaller, so the Reynolds number is equally enormous. So if you had a flow in a pipe with that Reynolds number of 10 to the 12 or 10 to the 10, for sure it would just be three-dimensionally turbulent. And that's, of course, exactly how people around World War I that time thought about the atmosphere, that it was in turbulent motion everywhere. But of course, the atmosphere is not in turbulent motion everywhere, except away from boundary layers. More or less, the atmosphere and ocean are devoid of three-dimensional turbulence. It happens very rarely. As you know, if you ever took a plane ride, and every now and then there's a bit of rumble as you fly through an active patch of turbulence, but mostly it's a smooth flight. So the reason, of course, is that the atmosphere is not a pipe, as is illustrated by this picture, which you might know. So the atmosphere is not a pipe, and what makes it so different from a pipe is, of course, I know you know all this, is that we're dealing with the two ingredients of geophysical fluid dynamics, namely stratification and rotation. And those two ingredients do two things. First of all, stratification inhibits vertical motion and tends to kind of broaden and weaken horizontal gradients, and then the rotation does the opposite. It weakens vertical gradients and kind of tries to inhibit sideways motion to some extent. So the famous Taylor column exemplifies this. But basically both of these strong effects tend to inhibit three-dimensional turbulence, and they also give the equations of GFT a very non-trivial linear spectrum. So instead of like having the linear spectrum of the Navier-Stokes equation, which is nothing, or viscous decay, we have a very rich linear spectrum just if you perturb the flow away from rest. So the next slide I know is irrelevant because Paola went through the derivation of stratified QG in the tutorial today. So this is just displaying the properties of that linear spectrum. There is a vortical mode with zero frequency in the simplest model. So when you do this, this is the mode in geostrophic balance in the horizontal. So the Coriolis force is balanced by the horizontal pressure gradient, and the buoyancy force is balanced by the vertical pressure gradient, and the vertical velocity is zero. So that flow, of course, then gives you the familiar pattern of kind of weather systems with highs and lows being encircled by motion in the kind of cyclonic and anticyclonic fashion that we're familiar with. And then the other parts of the linear spectrum are the inertia-gravity waves, which are fast. They have a frequency of at least f, as comes from this famous dispersion relationship, where the horizontal wave numbers and the vertical wave numbers combine in this fashion with the stratification frequency here and the Coriolis frequency there. And clearly there is a band of allowed frequencies which is always above f. So if the vortical mode has frequency 0, there is away from the equator a guaranteed frequency gap that allows you to distinguish these motions. And they, of course, are responsible for features like this, like an overturning gravity waves visible in this cloud pattern. Okay, so the simplest idea you might have is, well, if we want to understand something like the Gage-Nastrom spectra, we would like to understand how it is resolved into maybe these linear modes. How much of it is due to the vortical mode, the QG mode, and how much of it is due to these internal waves, right? That would be a nice thing to do. But of course, that's not so easy because we don't have the data everywhere that we can use this decomposition. We only have the data along a flight track. But we have many of those flight tracks, so we can average statistically. And that allows us to actually make a significant progress in that direction. Any questions so far? Good. Okay. So this is really then the outset of our approach to this puzzle. We imagine there is some kind of either plane or a ship traveling along, and as it travels along, it collects data of the velocity along the track and the velocity sideways and 90 degrees to the track. And here I will align the coordinate system always that it just goes in the direction of travel. So I'm not saying that x goes from east to west and that y is meridional. It's just aligned with the track, the flight track or the ship track of your vessel. And then it collects power spectrum of u and v and b along this one-dimensional transect. And it does that many times. You can statistically average, and then you get outcomes like this. So this is from actual measurement campaign, and this is an oceanographic data set, and you see there's some wave number spectrum here, wave number range, and there's the power spectrum of the velocity along the ship, 90 degrees away from the ship, and then the buoyancy all plotted together. And you can draw -2 there, but you still don't know what any of that means. Of course, you have to make assumptions. So we make assumptions that the whole process is stationary in time. It is three-dimensional homogeneous, and it's also isotropic in the horizontal, because we only have measurements in one direction. So we have to make that assumption in order to make progress. And then we can do a two-step procedure. The first one is we can, under these assumptions, perform an exact Helmholtz decomposition of the one-dimensional data. So we can split it into its divergent and rotational parts. I'll talk what that actually means. And then afterwards, we can also do a linear wave-vortex decomposition on that Helmholtz decomposition and find out how much of this data set is due to waves and how much of it is due to vortices under the made assumptions. So a tiny little bit of theory is inevitable at this stage, but the Helmholtz decomposition looks as follows. We assume that the horizontal velocity field in general given by a stream function component, which is non-divergent, and a potential, which is irrotational. And now you have to assume that the psi and the phi fields that are underlying this data set are statistically uncorrelated. Now there's an interesting story about that, whether under what circumstances that is actually justified, but it's not a bad assumption at first sight to assume that the stream function and the potential in your velocity field are uncorrelated. So then you can say if they're uncorrelated, then even something quadratic like the power spectrum can be split into a contribution due to the stream function and a contribution due to the potential, because the cross term would be 0 under this assumption of uncorrelated stream function and potential.
So Oliver, just a precision.
Mm-hmm.
So the track is horizontal actually?
The track is horizontal, yes. Sorry, I should have said
and
that.
so then you don't have vertical component?
Exactly.
Okay.
At this
so
point,
V is one component.
correct.
Is
so
a scalar, right?
So you have your ship or your vessel, and it's moving in the horizontal plane, and you're aligning a coordinate system with that ship track or flight track, and it's both in the horizontal plane. There's no vertical dimension here. Later on, there's actually a data set that also has vertical velocity, but again, it's only taken as a function of the horizontal direction. That is true. So we don't have to consider anything vertical at this stage. Thanks. Okay, so let's do some maths now. So we measure 2 fields, and we want to split them into 4 fields. So as 4 is greater than 2, we don't have enough equations for enough unknowns. So we need more information about these fields, and we can go back to some links between these spectra that you can find in Batchelor in 1953 and then Charney in 1971 pointed out that, say, if the spectra is entirely due to stream function, then the along track spectra and the traverse spectra are not independent, but they're linked by this differential relation. I don't find, even after having derived it many times and haven't written it down many times, I don't find anything obvious about this differential relationship. But maybe it is obvious that such a relationship should exist, because if you imagine there's a purely incompressible flow, so all there is a stream function, then surely both U and V must be generated from some kind of potential, some kind of covariance that just depends on the stream function. So they sort of belong to each other. There's only really one function describing the situation, and therefore there has to be some kind of auxiliary condition between the two that shows that they come from the same stream function. So with that understood, the particular form is non-intuitive, but this is the differential relationship that has to be true. And then, yes?
Sorry, maybe you said this before, but is K the a long track wave
Yeah.
number, or is it the magnitude? Yeah.
Yeah, K is the wave number. So the ship collects data, of course, just as a function of time, but then they convert the time sequence into a space sequence by just using the known ship speed. So what you get is a measurement that you treat as instantaneously taken in time along a line, and then K is just the wave number along the x-axis. So it's really a one-dimensional spectrum. Okay. C is the power spectrum. So the simplest way of taking this is if you measure U of x, say, along this track, then you can Fourier transform it and get U hat of k, and then CU of k is proportional. I mean, it's some kind of constant in front of it, the expected value of the magnitude of U hat squared. So you have to average over many tracks, and that's the power spectrum. I think, in geophysics it's usually denoted by SU. And you assume zero mean, absolutely. The stream function, everything is zero mean here. Any currents or something are ignored or have been taken out before you do this. Absolutely. Okay. So there's an auxiliary condition between the power spectra for U and V that come from a stream function. Then there is a similar looking one just with the roles and U and V exchanged if it comes from a potential. But now we can do some maths again, because now we have these two equations and we have these two equations. So we have 2 plus 2, and that's equal to 4. So that's good news, because that means we have 4 equations for 4 unknowns. Or we can just substitute these relationships into this box, and we suddenly obtain a 2 by 2 set of ODEs that allows us to solve for these components in terms of the known right-hand side, which is what we observe. So the procedure is very simple. You have a boundary condition at infinite wave number that the spectra are all 0, and then you integrate from infinity to 0, integrate these equations backwards in K, and you end up with your Helmholtz decomposition. Yeah? So it's a simple and exact statement. Yes?
Sorry, the notations are not very clear to me. So the one in the red box.
Yeah.
So C hat U is equals to, like, is it like a partial derivative
Oh no,
respect
sorry.
to
This is the power spectrum of the along track velocity.
So then what is psi and phi on the right hand side?
So we conceive that the power spectrum of U consists of two parts, one that's due to a stream function from here and one that's due to a potential. And if we assume that these potential and phi, the potential and the stream function are uncorrelated, then even something like the power spectrum, which is like the square of the velocity, or the covariance function, which is like a square of the velocity, once you take the statistical expectation, the cross term disappears, and you can say it makes sense to talk about these things as being a sum of a stream function, a potential part. So there's absolutely no derivatives involved here. This is simply using C as the covariance, the Fourier transform of the covariance function, really, which is why it has the little hat. And then you try to split it into these two parts.
And how do you arrive at the next two equations?
These ones?
Yeah.
Yeah, this is a transparency I skipped. I'm happy to show you the calculation. It's simple. You need to write down the covariance, the power spectrum of the stream function, and then you see how the stream function covariance relates to the covariance of its y derivative and of its x derivative, and then you take a one-dimensional version of this, and then you see that there's this differential relationship. It's like 3 lines, but I'm happy to show it to you otherwise. But as said, so it's these kind of relationships come up in the theory of incompressible turbulence, where they exploit these kind of relationships that come from the continuity equation, and Charney realized that it plays a role in 2-dimensional flows and can be used. Okay. So that's the first thing, that the right-hand side is observed, and then we can solve this and have an exact solution for the Helmholtz decomposition, and that's we published that in 2014. This algorithm. And so the quantity of most interest is the kinetic energy. So it's a sum of U and V power spectra, and so we can also say we have now decomposed that into a rotational part and a divergent part. And well, our solution gives these parts, and Lindborg, who was a reviewer of our paper, noticed that if you do one more line and just add these two functions together, you get a simpler expression, which is this one. So he published that, which is very nice. Of course, everybody uses these expressions, but I do want to point out that they're absolutely identical to our exact solution, both analytically and numerically. But it means that you observe. It's really nice that you observe these fields directly. This is directly what the people from the ship give you, and then you just stick it into this integral, and out pops the kinetic energy due to the stream function and the kinetic energy due to the potential. I mean, it's kind of mind-boggling how easy it is. And all the theory has disappeared. So it's a simple, cheap, exact, and useful result. And we don't often get things like that have all those 4 properties. Yeah, that is helpful as well. That is guaranteed for the exact spectra. It is a problem for the observed spectra, which of course have errors. What happens in practice is that the finite length of the track provides a cutoff for low k, and so we integrate from infinity down to the lowest possible k, which is something like 2 pi over the length of the track, and then it kind of that helps you not falling off there. So that's one step of the washing cycle, getting this exact Helmholtz decomposition, and then the second one is, well, we can use what we know about linear wave theory. I already had the dispersion relationship. Here are some more equations that you can use to notice that the power spectra of buoyancy and the power spectra of the vertical velocity are related in a variety of ways. And if you put this all together and use the properties of plane internal waves, you'll find some kind of energy partitioning law that tells you that the potential energy plus the kinetic energy due to the stream function is equal to the kinetic energy due to the potential plus the vertical kinetic energy. It's simply a property of plane waves. And as we've assumed homogeneity in the z direction, we can conceive of the field as a superposition of uncorrelated plane waves, and therefore this actually holds for each constituent in our system. And then if we integrate over L and M to get a one-dimensional spectrum, we get this simple relationship that the buoyancy spectrum along the ship track due to the waves plus twice the kinetic energy in the psi field is equal to the kinetic energy in the phi field plus the vertical kinetic energy. And if we now reduce this, so this is the same formula again. If we say we have hydrostatic waves so that we can ignore the vertical velocity, or if we can measure it, then this results to an even simpler statement like this. And then, and this is the final and truly amazing cancellation, if we define the wave energy spectrum to be the sum of the x velocity due to the waves, the sum of the y velocity due to the waves, plus the buoyancy due to the waves, then it turns out if you combine this with these relationships, that the energy spectrum due to the waves is simply equal to twice the kinetic energy in the potential part of the flow that you've just discovered. So I wish I could say that we were so clever that this was all clear to us. However, it was completely unclear to us. When we had this, we assumed that the waves had some particular frequency, some constant, and tried to analyze it based on this. And at the final analysis, the value of that assumed constant always dropped out. And after that happened 3 or 4 times, there was enough motivation to actually see whether there was something else going on. And we finally realized that this actually was going on, that we could decompose it, and it didn't matter what we assumed about the frequency of the waves, because this partitioning law helped us out. But what that means is now that we can compute the energy wave, the part of the observed energy due to the waves, simply from observing the horizontal velocities. So this is now this is an example now how this works. This is the same oceanographic data set that I showed before. Here's the raw data. So here's the inverse wavelengths, and here's the velocity along the ship, sideways to the ship, and the buoyancy. And this is what the raw data tells you. And to me, it doesn't tell me very much. This is k to the minus 2 slope maybe, but it doesn't tell me whether these are waves or vortices or anything in between. So the first step is to use this data in velocities and do the Helmholtz decomposition. And we already see then that the divergent part, the part due to the stream function, dominates at large scales and then gets undercut by the growing importance of the phi field. But then if we also do the wave-vortex decomposition, we get this very nice result where E is the total observed energy and EW is the diagnosed wave energy, and we see that it fits like a glove for all the scales below below that point, which is something like 100 kilometers, and then it tails off, so the rest of it is due to the geostrophic motion. So that was contained, that was a fingerprint somehow hidden in this data that is now very apparent, right? You have under the assumption of linear theory, you have this very straightforward result here, that this particular data set seems to consist of waves, seemingly linear waves, at scales below 100 kilometers.
So how do one get this data at a depth of z equal 200 meters from a ship?
I think this is an acoustic, you may know this better, Raf, but I think it's an acoustic Doppler profiler. So it's an instrument that's in the hull of the ship and can sort of see down, and because of this, the water is dirty, it can kind of track various bits of motion in the water, and because it's more than one beam, it can do it at various depths. And so it's a kind of continuous data collection system, and it actually has more than one depth, so you can kind of pick when you look at this data whether you want 200 meters or something else. It has a certain range that it can do. I believe that was where that data set came from. Okay, so the easy bit is always, to measure the velocities. The buoyancy cannot be observed with the acoustic Doppler instrument, so there was a towed instrument that also measured at 200 meters the buoyancy. So in order to get the total energy, you need the buoyancy. In order to predict the wave energy, you actually don't need the buoyancy from our theory. You would only need the horizontal velocities. But that
so you have a crossover at 100 kilometers. Can you?
That's what it looks like, yeah.
Can you explain why this length?
No, that's the great thing. I have no idea. That's why this is such a great method. You don't have to understand anything. No, you can now think about why should the waves dominate from then on or something, right? This makes no statement about the cause of this. In particular, there's no implication that there's a cascade of anything in any direction. It's purely analyzing the data under the made assumptions. So. Yeah, so the question is, if once the waves dominate, wouldn't there be nonlinear interactions that probably render these kind of assumed independence or uncorrelatedness between phi and psi problematic? That might well be true. We can show that for a linear wave field that's stationary in time and has no preferred direction, that indeed a wave field has both a psi and a phi component in a rotating system, but those are uncorrelated on the linear dynamics. If it is a strongly nonlinear effect dynamics, then it probably would not be the case. On the other hand, all our analysis is kind of based. Yes, so yeah, so my feeling would be that what's likely to go on is that the flow is close to linear dynamics at any moment in time, but the overall evolution of the linear amplitudes is affected by nonlinear interactions that can that can move the energy around and create various effects. Nevertheless, it is probably possible, even for such a scenario, to have at any moment in time stuff that is very well diagnosed by just using the linear eigenvectors. That's sort of most I would say to that. But as I said, at this level, it's simply a diagnostic that shows what you can get out of it if you just assume the linear dynamics or the linear eigenmodes. So let's now return to the Gage-Nastrom saga. So like all good sagas, there's sort of three parts. So the first of it is, of course, we can just apply our method to this data set, or rather to the mosaic data set that came later and is easily available. So when we do this, we get part one of the saga. Oh no, sorry, we don't get part one of the saga. Oh, this is just repeating what Ted, I think, talked about, is that there's no shortage of explanation models for why there is a break in the spectrum and why the small scale spectrum is k to the minus 5/3. So it could be isotropic 3D turbulence, but we already know that this is not a pipe, so that's not really likely. It could be a version of what's called stratified turbulence, cascading energy downscale. So it would be a nonlinear cascade. Could be upscaled balance flow energy, or it could be modified balanced downscale energy. There were suggestions like this. Could be surface causal geostrophic, or it could just be internal gravity waves. So all these possibilities. And this is our first take of just taking the data. This is the observed spectra. So longitudinal means in the flight direction, transverse means 90 degrees, potential energy. So it's not, so it just shows the minus 5/3 at small scales and minus 3 at large scales. And then we do the Helmholtz decomposition first. And what I like about this is that the red bit, which is the contribution due to the stream function, dominates at large scales. Then it sort of tails off, and the blue, which is the divergent component, comes in, and there's a tiny little bit of crossover, but more or less they're sort of equipartitioned at this stage. So you don't get a very clear signal by just looking at the Helmholtz decomposition, because it just looks, oh, okay, there's both a divergent component and there is a rotational component, and maybe they're comparable at these small scales. However, if you do the additional wave-vortex decomposition step, you get this picture, which is now black is the observed total energy, and blue is the diagnosed wave component, and you see that it more or less hugs the observed energy, and then the residual geostrophic component is much less. I mean, logarithms don't add, so this is actually more impressive than it looks. The diagnosed wave energy is significantly larger than the residual geostrophic one. Yes, please. You have to press the button.
So from this picture, don't you think the red curve is a signature that there are a lot of nonlinear interactions because geostrophic modes or vortex mode are losing their own geostrophic dynamics? They're no longer -3, so maybe energy is becoming like there is more nonlinear interaction, and eventually there is more equipartition of energy between the wave modes and vortex modes. And considering that we have, for each wave number, we have 2 wave modes and one vortex mode, they're always more energetic than.
Well, I'm glad that you swallow the main message immediately, that this is all internal waves. So, I mean, you might well be right? There might well be, I mean, if this is correct, if this diagnostic is actually correct, that the bulk of this spectrum is nothing to do with the balanced flow anymore, it's imbalance in the form of nearly linear internal waves that might be guided nonlinear by further interactions or something, then we're in business. I mean, that would be then the paradigm under which to think about this, and hypotheses like you just formulated, they might well be something to look at, right? But first you have to believe this, that this is actually the explanation. So let me go on to the other 2 pieces of the saga. So basically this was all the data. The airplanes, they flew, obviously commercial liners fly near the tropopause. and they've sort of the range of altitudes was sort of between 9 and 12 kilometers. And what happens is that all these flights were just averaged together, but because of the density decay, the kind of power spectra of velocity were all strongly influenced by the highest flight track. Because of the density decay, the velocities were higher up. So actually this data set, if you just average everything together, is strongly dominated by the flight tracks in the lower stratosphere, whereas the flight tracks in the upper troposphere are kind of getting short shrift. So if this is the tropopause, the plane might be flying in the lower, in the upper troposphere, or it might be flying in the lower stratosphere, and basically the flight tracks up here dominate over the flight tracks down there because of the density decay. So you can try to split them into stratospheric and tropospheric parts. And so T here is for troposphere. I think this was done using ozone as a distinguishing feature between the troposphere and the stratosphere. And then the picture changes. In the stratosphere, in the lower stratosphere, you get exactly the same as before, just the color code has changed here. So the wave field in red hugs the total energy, whereas the vortical field drops off at the transition scale. But in the upper troposphere, not so much. It seems to be like 50-50. And this is a bit of a puzzle, because I mean, Ted mentioned that, oh yes, as you go higher up in the stratosphere, because of Charney filtering, the balance component drops off more and more. But these flight tracks aren't very far separated. There might be a kilometer between them. And so to get such a big difference in the diagnostic poses really a big puzzle. So we try to use linear theory and the fact that the stratification jumps at the tropopause to kind of get better understanding whether it's possible to have the same field on both sides of the tropopause and get this result on one side and that result on the other side, but we couldn't really get a very convincing answer. But then another data set arrived, which is a high START-08 is a high resolution research flight mission. So it wasn't commercial airline, it was an instrumented research plane. 5 minutes already? No.
No. I missed one point about the analysis.
Yeah.
Is that how do you define the buoyancy frequency? How you choose in case where it can be strongly non-linear? And do you need to assume some homogeneity for the waves on the vertical?
So I know more about the second part of your question. So how to get the n squared, I think either came from the flight track or it was from atmospheric data that was available for that time. I don't know. As no special effort was made to get n squared. It was simply taken somewhere either from the data set itself or from analysis of the atmospheric data at that time and location. The second question is much more tricky, which is why we assumed in the original version of the theory that everything is homogeneous in the vertical. If you have a tropopause where the stratification jumps by a factor of 2, that's manifestly not the case. Your environment is not homogeneous in the vertical. So we tried to adapt the theory for that, even though at sufficiently small scales it shouldn't really make any big difference. So we did play with this. And it's obviously one of the possible causes for disagreement. But as I said, while we were still kind of struggling with this data set came around. And if you take this data set, this high resolution data set, it's now a full decade further down. It goes down to 1 kilometer, whereas the mosaic stopped at 10 kilometers. It doesn't go as far up as the mosaic data, but there is a decade of overlap. So it's a bit like matched asymptotics. If we look at the stratospheric data, there's a wonderful agreement. Here's where we only have start data. Here's where we only have mosaic data. And then these two data sets agree beautifully 20 years later in the overlap region. Not so much in the troposphere, where they overlap. The start data kind of doesn't really agree with the mosaic data. So if you now analyze the start data, so that's part 3, so now suddenly everything looks exactly the same as before. Both in the stratosphere and in the troposphere, the data seems to be perfectly explained at small scales. This is now only the small scales, from 100 to 1 kilometer, seems to be perfectly explained by the wave spectrum. So we're sort of back to that we don't understand why the mosaic data disagrees with this, but this is high quality data taken over the continental US. So at the moment this is the best available thing, and it seems that now the riddle or the kind of discrepancy has disappeared. In all locations, tropospheric or stratospheric, it seems that the available data is well explained by linear wave theory at the smaller scales. Okay. Yes. I mean, I don't know whether you're allowed to ask a question, but
so the horizontal scales are fairly large, actually, so I guess they must be resolved in models or reanalysis and so on. So, I mean, do those people have the same impression that it's full of linear waves?
Well, so they certainly have observed breaks in the spectrum now. It's strange that even though they have published these results, I mean, there are papers out there, and Ted mentioned a few about these GCMs, they haven't come up with a clear answer to what actually causes that spectrum. So this can't be far off, but it hasn't happened yet. I mean, one problem is one advantage of this method is that it just uses local data. Right? If you do this with a GCM, and for example, the data that Ted showed was in a spectral was for a spherical harmonics index, was the one-dimensional spectrum in terms of a spherical harmonic index, which is globally averaged and lumping everything together. So that might be one of the reasons why it's not so easy to make a statement from the GCM, because they have, if they actually try to resolve it into modes and find whether it's waves, they would have to use global functions to do this, and then it might not jump out so much. So some kind of analysis that only looks at a local patch of data would seem to be necessary to do this. That's my best answer. It's definitely true that the GCMs nowadays, when they run at full tilt, they do produce a break in the spectrum. Okay, so that brings me to the end of that part. So it's just a few papers that are to do with this. So the basic theory was laid out in this 2014 paper, and then there were various applications, first time and second time, to the atmospheric data. And now, as said, everything is based on horizontal isotropy, but recently had a version that can extend this method for horizontal anisotropy of a certain kind. You can't treat the general problem, but you can treat a fairly well-defined version of this. Okay, so that's as much as I wanted to say about that. So let me then switch to the second bit, which is this work in progress, which is, so here the working title for this paper is Wave-Induced Mean Flows in Rotating Shallow Water. And so rather than thinking about linear decomposition into waves and vortices, we know, of course, that waves and vortices interact nonlinearly. If they're both of small amplitude, then this interaction will start at quadratic order in your small amplitude parameter. And Ted described the kind of classic theory for wave mean interactions in his lectures, and they dealt with sort of zonally symmetric mean flows. I mean, mean flows that come from averaging around latitude circles and that are very strong, like the jet stream, 100 meters per second. And that theory began sort of in 1960 with the publication of Eliasson and Palm, their famous flux vector. And then it more or less, by the 90s, it was complete. I mean, sort of everything there was to know after rapid progress had been sorted out. And much less of that is true for the problem where you can't average zonally. For instance, in the ocean, where the continents get in the way in most places, and also where there isn't really any strong mean flow. I mean, as both Raf and Bill spoke about today, I mean, strong oceanic flows are like 1 meters per second, not 100 meters per second. So there isn't such a dominant mean flow that would lead naturally to this kind of classical theory to be applicable. So much more attention is now paid to the case where the kind of the scales of the waves and the scales of the vortices overlap, and they don't just overlap in spatial scale, they also overlap in amplitude, that not one of them is much stronger than the other, and that this kind of things all happen together. So there hasn't been really a general theory that has emerged on how to deal with this, at least in my understanding. Potential vorticity thinking is definitely important in this field, and in the absence of a general theory, what we should really do, we should investigate as many model problems as possible to build our intuition. And one of these came out as a kind of a special case of what Jim was studying for his PhD, which is a tractable special case when there is no PV whatsoever, no PV contrast. The PV is simply uniform, so all there is waves, but you can still create mean flows out of this. And how to do this when you have kind of local wave patterns is the topic of this section. So we've all seen the rotating shallow water equations. So it's a two-dimensional velocity field, material derivative, Coriolis force. We're on an F plane here, and then the gradient times gravity times the gradient of the height field, and then the continuity equation for the height field. There is a potential vorticity, which is the absolute vorticity divided by the height, and then the material derivative of this field is precisely 0. And what we want to study is a special case where this PV field is precisely equal to its background value, which is just the constant f divided by the constant h, which is the kind of undisturbed layer depth. And then if this is true initially, by that equation it will be true at all times later. So we can in fact say, well, this is always the case, and we can substitute from this relationship, and we get that the curl of u and the height field are always slaved together like this. And that sort of reduces the dynamics by sort of 33%. So all vorticity is ballerina vorticity that came up today already. So a cyclone is associated with an increase in layer depth, which is easily distinguished from a balanced flow because it's exactly the opposite of balanced motion, where cyclonic flow would be associated with a depression. So if we study linear waves, we just linearize these equations around rest, and we get these equations. And then we get the dispersion relationship for plane waves, which already Antoine and other people have shown. So omega squared is equal to the Coriolis parameter squared plus this non-dispersive bit that becomes more important for small scales. Okay, so that's linear theory. Now we want to understand how these linear waves on the quadratic level force a mean flow. So we need to go back to the equations and go to the next order. And there's a variety of ways of doing this. And what's important to realize is that what we're really interested in is not so much the Eulerian mean flow that comes from averaging the flow locally, say in time, if you have a fast wave, but we're really interested in the Lagrangian mean flow. And if you're an ardent student of surface waves and you have a propagating surface wave, then you know that you can get different answers if you average, say, the horizontal velocity at this point and just average, it might be 0. It's possible. But if you average following a rubber duck, okay, it's not a very good rubber duck. Okay, it's an abstract rubber duck that kind of oscillates around this point in this circular fashion that's typical for these surface waves, then the velocity that's experienced by the rubber duck will not be the same as the velocity that you get from averaging at a fixed point. It will experience a Lagrangian mean velocity, which is the sum of the Eulerian mean velocity plus a Stokes correction, which you can easily compute from the linear solution. And that's in the textbook. And you can do that for any field you like. And this is really the velocity that moves stuff around on average. So we kind of conceive of the motion of any particle as something that wobbles back and forth, but also has a perceptible drift. So we are really interested in the velocity that describes the tangent to this mean line rather than the rapidly varying trajectory that goes around there, and certainly not something which comes from averaging over many different particles all at the same location. So all you have to remember is that L is equal to E plus S. The Lagrangian mean flow is equal to the Eulerian mean flow plus the Stokes correction. So with that in mind, we can analyze the equations with that aim. So we simply average the equation, sort of Reynolds average Eulerian style, and that gives us these terms plus the Reynolds average over the Eulerian average over this u dot grad u term. And then if we don't want u bar but u bar L, we simply add Stokes drift terms. So we need to add an f cross u bar S on both sides, and we need to add a time derivative of the Stokes drift on both sides. And now on the left-hand side, we have only mean flow quantities. On the right-hand side, we have lots of quantities that we could, in principle, compute from the linear solutions. However, we're not satisfied with this form. So sometime later, we arrive at this equivalent form, where there's now a quantity which is a vector pseudomomentum, which generalizes the one-component zonal pseudomomentum that Ted talked about. And there's also the gradient of the Stokes correction to the height field, and there's a second time derivative of the gradient of the linearized particle displacement squared. So in that form, we want to actually analyze this equation. And we can do similar work for the continuity equation. So there's nothing magical between these two. It's just a question of taste and kind of foresight, which form will be the most convenient to actually figure out how you're going to force the mean flow with these wave fields. So when we do this, oh yeah, this was a reminder that I wanted to draw a picture of the situation we actually computed now. So these are the equations, but as I said, the important thing is not so much to write down the equations, but to solve them for particular cases. So we're now looking at a slowly varying, wave packet. say in this theory aligned with the x-axis. So the wave packet has a fairly short wavelength, but then a much larger envelope, and as a whole the wave packet moves from left to right through our domain, and we're trying to find out what is the actual response of the mean flow to this wave packet. What's the actual flow if you put a lot of rubber ducks down? How will they actually experience the passage of this wave packet? Obviously they will wobble back and forth in response to the direct oscillation, but there will also be a slower drift pattern, and that's really what we want to do. Okay, so now we need to use that equation to actually compute this. This is now easy for us because this is a Helmholtz decomposition again. The Lagrangian mean flow is split into a stream function bit and a potential bit, all decorated with indices L for Lagrangian, such that the curl of u bar L is the Laplacian of the stream function and the divergence the Laplacian of the potential. And we can do the same thing with this magical pseudo-momentum field and decompose it into a potential and stream function component. And again, this is all known from the linear solution. And then this is the equation actually governing the curl of u bar L. Well, there's some operator here, which is the wave operator, and then there's a bunch of stuff on the right-hand side. If you approximate this equation by steady wave packets, so you kind of arrange sources and sinks that this wave packet becomes steady, then you get a simpler form because you can drop all the time derivatives. This was done first, I believe, some stuff coming out of my thesis in 1998, except there was a mistake for strong F, but no one seems to have noticed. Anyway, we corrected this now in this work. So if you ignore all the time derivatives, you can get this equation, and then you can solve for the stream function. I give it an index 1 here so to denote the steady approximation in terms of the stuff on the right-hand side. If you don't ignore it, you can solve for the part of the solution that travels with the wave packet by saying the time derivatives are equals to minus the group velocity times the x derivative. So if you do that, then you can transform this equation into a frame of reference moving with the wave packet, and you look for a steady solution in that frame, and you get that equation. That's not the same equation as this one. And then you can also get similar equations for the divergent part of the Lagrangian mean flow, but I'm sparing you their shape. They look sort of similar. And then Jim heroically did a direct numerical simulation so that we could compare the predictions by the theory with numerics. So these are 3 sets of experiments. This is with very low rotation, very weak rotation. The middle one is with moderate rotation such that the deformation radius is comparable to the wave packet envelope. And then the last one is done with strong rotation such that the deformation radius is comparable with the actual wavelengths of the wave packet. And in the first one, you get what's already computed in Bretherton in 1969. You get some kind of dipolar return flow where blue is negative, so this is a cyclonic return flow on the side of the wave packet. Sorry. Oh yes, Jim also, in order to make life hard, rotated the wave packet by 45 degrees and did this on a Cartesian grid, so it was particularly bad, hard to resolve, but he got it to work. So the wave packet is actually bang in the middle here and is propagating at 45 degrees.
So can you explain what is on the plot? So it's the Lagrangian.
Oh, sorry. Yes, absolutely.
So and where is the wave packet? I mean
exactly. So we're looking down at the domain. The wave packet at this moment in time is in the center of the domain. It's not visible, but what's plotted here is psi L, the stream function for the Lagrangian mean flow. So if you take its gradient and rotate it by 90 degrees, you get the rotational part of the velocity field. And then this is kind of dipolar return flow here, which is kind of the classic response, and this is the asymptotic theory, and this is a direct numerical simulation. The agreement is so good that I'm slightly worried whether Jim plotted the same field twice, but let's assume that's not the case. Anyway, this is the asymptotic result, and this is the asymptotic result. This row is the direct numerical simulations, and this is the steady approximation. And the steady approximation is fine if there's no rotation, because I mean, for very simple reasons, the only thing you can get then is this dipolar return flow. As you crank up the rotation rate, the dipolar return flow kind of transforms into something that's dominated by an anticyclone at the location of the wave packet. So that's the asymptotic theory. Again, this is a direct numerical simulation. And then the steady approximation doesn't quite get this. It does get an anticyclone, but it's much weaker than in the true answer. And then for very strong rotation, the true solution is a strong anticyclone, but there is, maybe you can't really see it, there is some stuff outside the wave packet as well, whereas the steady approximation gets something which is compactly supported where the wave packet is, which is very reminiscent actually of the result that Wagner and Young got for the mean flow induced by a mode 1 disturbance in a three-dimensional Boussinesque model with strong rotation. And I think the reason why that is the case is because on the one hand, a mode 1 wave in a three-dimensional system is a bit like a shallow water system, and secondly, their scaling kind of made sure that the wave packet was extremely slow, and therefore I think the steady approximation definitely holds. So maybe that's the reason why it's so sharply compact. I'm not sure whether if you redid that with allowing for faster wave packets, whether you would pick up something like this. It's a bit hard to tell, but it's it could be one thing or the other. Yes?
Sorry, just to make sure I'm following. So you're plotting the potential function, is that right?
The stream function, sorry. So say the x component of the Lagrangian mean flow would be minus the y derivative of the stream function plus the x derivative of potential, and both are there. I'm not actually showing the potential. We also computed the potential. So this is one part of the response.
I was just going to say that field right there looks like
this.
The potential on the left. Yeah.
Yep.
That looks like flow past the sphere for the potential function. But I guess that's the exact. That looks like the analytical solution for flow past the sphere.
Yeah, I think it's simply it's a dipole, and in that sense, you sort of many things look the same. I mean, you're absolutely right. I don't think there's anything much deeper than that. These are kind of dipoles, and then there's some kind of monopole clicking in there. I'm not sure there's anything more to it. It is true if you actually, if you combine this with the picture for the potential, actually, it's also funny. It's kind of rotated by 90 degrees, and so maybe there's something to it. But I mean, certainly, it's difficult in the end. You're sort of inverting things like Laplace's equation, and so it's sort of difficult not to get things that look like monopoles, dipoles, quadrupoles. In the end, there isn't much more. Yes. So it's okay.
You don't show us the potential because it's less interesting, or it has as large a magnitude, and is it associated with interest?
I'm not showing the potential because I still want you to read the paper once it comes out. No, I simply didn't put it in. The potential, first of all, in the steady approximation, the potential is precisely 0. So you wouldn't have that row. In the non-rotating case, the potential doesn't settle down to a steady state, but it forms a shock and a bow wave, so this panel isn't there. And then otherwise you get kind of patterns that complement this in the others that you can produce. It also works out, and it's interesting. But I didn't want to include that here.
I just wanted to ask, so we're using the Lagrangian definition of the mean because does it have anything to do with the material conservation of PV, or?
Oh yes, I mean this is the Lagrangian mean velocity would be the one that would be advecting the Lagrangian mean of the PV without any further disturbance. So it is really because it's the velocity field that is truly responsible for the kind of cumulative advection. So any kind of advective field like PV would be advected by the Lagrangian mean flow, not by the Eulerian mean flow. Exactly. Which brings back to the don't think about the Farrell cell bit that Ted said. Okay, so I'm conscious of the time, so let me just finish by we also did standing waves. So we assume that the height field is just a cosine omega t times a height function h hat, which is real valued. That will solve the linear equations provided it's an eigenfunction of the Laplacian with a certain eigenvalue. And then you can work out that the velocity is of this form. And it's very nice that, I mean, Antoine Venais, he spoke about if there's no rotation, then zeros of these equations, zero lines, I mean, happen on lines. And you can see that if you only have this term, then say the x component will be 0 wherever hx is 0, which will happen on a line. But if you have rotation, then in order for both the coefficient of sine omega t and cos omega t to be 0, u prime will only be 0 where hx is 0 and hy is 0. So that will be the intersection of two lines. So and you get this thing that the velocity only vanishes on points in the rotating case. It's nice that this explicit solution illustrates this comment that Antoine made. And the other nice thing is that you can compute the Stokes drift exactly, and it gives you this answer. You can compute the pseudo-momentum exactly and gives you this answer. It's not the same as the Stokes drift. And then you can compute the steady Lagrangian mean flow as before, and you get this equation. And the interesting thing is that this is 0, the right-hand side is 0 if f is 0. He has an explicit f here, but if he follows through what p is, there's also an explicit f there. And if that's 0, then both forcing terms on the right-hand side are 0, so we get that without rotation actually nothing moves. So unfortunately we couldn't think of any smarter eigenfunction of the Laplacian as cos x cos y, so sorry, it looks a bit boring. But this is the plot for no rotation. Again, it's a theory and numerical simulation, and simply there's no flow in this case. And then there's the strongest flow at some intermediate rotation, then it decays. So the final picture here is this, that we varied the rotation strength whilst keeping the energy in the waves constant, and then for the wave packet that gave us monotonically decreasing energies in the mean flow, so compatible with ideas that the more Coriolis force you have, the more the flow is kind of choked and slowed down. But for the standing waves, there was a 0 at the non-rotating limit, and then there's an intermediate maximum at some intermediate wave rotation rate, and then it tails off and quickly decays. I mean, this is a logarithmic scale, and this is a linear scale. So that's as far as we got. With this came as a surprise to us, because all the cases we studied before and that other people have studied, they always showed this behavior, that the mean flow kind of tails off the more rotation you turn in. So it's clearly, there's at least one counterexample to that. Okay, that's all I wanted to say.
So I have a question on the first part of the talk.
Okay.
So you used the dispersion relation for the waves, and I was wondering, even if the waves are linear, you could have some Doppler shift in the dispersion relation from the larger scale flow. Is that negligible for these problems?
It is neglected. Whether it's negligible is the question, right? So certainly we are using the linear decomposition relative to state of rest. So there's no attempt made to cater for the for Doppler shifting. Yeah.
Can you go back to when you derive the mean flow equations? So there's no approximation done here, right?
Well, this is to second order in wave amplitude, but apart from that, there's no approximation. So these are the full equations at second order in wave amplitude.
And then how do you get your dash fields?
My dashed fields. So for these, you mean all of these guys?
Yeah, yeah.
Yeah, so for these you actually have to solve the linear equations. So
the linear ones,
so
though.
you can either assume a wave packet and then you...
The linear ones, not the non-linear. Okay.
Exactly. Okay. So these are all... these are all just done using linear theory, and then their square gives you the entrance to getting the mean flow correct at second order, but only at that order. And then after that you would have to take the back effect of the mean flow onto the waves into account, etc., etc.
So I have a naive question about the Helmholtz decomposition. So you mentioned the assumption that the stream function and the velocity potential are uncorrelated. So to what extent the assumption holds true?
So that's an excellent question. So basically our point of view was, as far as the waves and the vortices are concerned, we simply assume that they're uncorrelated on physical grounds, that the waves don't really care about there being vortices, and the vortices don't really care too much about the waves, which seemed like a reasonable physical approximation to get going. The difficult thing is that the wave field itself has, in the presence of Coriolis forces, has both a component that's in the stream function and a component that's in the potential. And it's not at all clear when you look at the wave equation that those two, if one of them is a random function with a given measure, that the other one is uncorrelated is not obvious. We could convince ourselves that if you have a stationary situation and that waves are equally going in each direction, so they go just as much in that direction as they go in that direction, then you can prove that the stream function and the potential of the wave field are actually uncorrelated. But that's as best as we could. Yeah, I'm sure. I mean, doesn't yet apply to superconductors, but we're working on it. No, I mean, absolutely. This is part of the, I mean, the first bit, I mean, so, I mean, Han, who's here, has pushed us a little bit further looking at the ageostrophic correction to the quasi-geostrophic flow, which is also a potential then, and investigating the conditions under which you can guarantee that those two components are uncorrelated. And we found some criteria, but it's not completely straightforward. But it seems that a reasonable approximation, you can start with this, the uncorrelated. There's no obvious counterexample that jumps out, although of course you have to be careful.
Okay. If I understand, like you're following this wave packet, which means that it's an order 2 response. The mean flow is an order 2 response of the wave amplitude.
Yeah.
In terms of the wave amplitude. So when you look at this wave packet, you have some net motion and then it stops. So there's no mean flow left behind the wave packet.
So in our simulation, the wave packet didn't stop. I mean, we can only follow it that far along in the simulation, but it's sort of like a few hundred primary oscillations. So it suddenly get moved from the lower left corner of the domain to the center point, and it's kind of long enough for that. So it didn't disperse noticeably, and it didn't dissipate noticeably. It was a pseudo-spectral code that was relatively well suited to keep these waves honest for at least a few hundred oscillation periods. So what happens when this wave packet dissipates or something is a different story, and that's interesting as well. But in this case, we tried to keep dissipation to an absolute minimum that we could get away with.
So I have a question. Why isn't there any term that involves the correlation of U prime and H prime, which is maybe the same as Z prime?
That's because I didn't show you the continuity equation. So in the continuity equation, you naturally get an H prime U prime term, which is different from the Stokes drift term, and which you need to take into account if you want to solve the whole problem. So I showed you the momentum equation. In order to get, say, the equation for the divergence of it, you need to bring in, you take a second time derivative and substitute from the continuity equation, which I didn't show you. So the H prime U prime does come in from the continuity equation. You need to use that as well. I just didn't show it here. But you would treat it fundamentally the same way as all these guys. H prime and U prime are simply known from the linear solution. You just need to do the right thing. But yeah, it absolutely plays a role.
Question on the wave vortex decomposition. If we add the two-dimensional spectrum of the pressure, would it be possible to have the wave vortex decomposition for the pressure spectrum?
I think if you add something more to this data, given that we can already decompose it, we can probably, I would guess that we could predict the pressure spectrum that belongs to the waves from this, because we now have we have diagnosed the waves. So to that extent, I think one could check that. I'm not sure that the pressure is ever measured either in the aircraft or in the ship data. I'm not sure. Well, sea surface height. Yeah. Directly at the sea surface, this might be a little bit difficult. I haven't thought about it because, again, you can definitely do the Helmholtz decomposition, that's no problem, but to do the wave decomposition again, we sort of assumed vertical homogeneity, which if you add z equals 0 and the density below you is 1000 and the density above you is 1, it's not really vertically homogeneous. So there's you would have to kind of modify the model to allow for this, to use sea surface height directly.
Okay. So you mentioned that the SR08 data set was from flights over continental US,
yes,
right? How about the Mosaic data set? Was it also from just flight over land, or it included transatlantic or transpacific flights?
I'm pretty sure, I'm not 100% sure, but my understanding is that the Mosaic data is again the same deal as the GASP data originally, which is transatlantic flights, instrumented commercial airliners, and a lot of them. And as most of them then fly the 3,000 miles across the Atlantic, that's really the data set. In some sense, that's, yeah. You could say maybe over the continental Europe, continental US, there's more topography, then maybe there are more waves to begin with. That's certainly something one could. Right. Okay. Yes. Thanks for the reminder. I have to read our own paper. That overlap region I showed you. Some of the Mosaic data was over the continental US, and even there, it seemed to be. It seemed to be not look any different. Yeah.
I had a question. Have you ever taken these one-dimensional transects in a model, calculated it, and where you know the exact decomposition, so you can evaluate whether it fails or not?
I haven't. I think
under what conditions it fails.
I haven't, but if you do this on a model and the assumptions of the model, it's it's just mathematics. It has to work, right? And otherwise, if you have an interesting experiment that doesn't satisfy these
model
things.
with nonlinear dynamics where you
Yeah.
could have a correlation.
Yeah, so no, I haven't done it because I don't have a model that can do it, but I think that would be interesting clearly to figure out when does this fail. I mean, it has been tested a little bit in this method when they have alternative ways of decomposing it. It seems to have worked, but yeah, that's obviously something that would be useful.
Sorry, just a naive question. Some of these H's have superscripts and some don't. Is there a reason for that?
So the superscript L is Lagrangian,
Yes.
meaning that instead of, say, averaging the velocity field at a fixed location in time, you average it following a particle that's being jiggled around by the wave motion. And that gives you a different answer, and the discrepancy is the Stokes correction. And you need to add that to the Eulerian mean flow if you want to get the Lagrangian mean flow. And you can do that then for any other quantity. So this is H averaged in place. This is the Stokes correction you would have to add to H to get the Lagrangian. I do want to point out there's a factor of 2 here, so you can't simply put this on the left-hand side and get the gradient of H bar L. It doesn't work like that. But yeah, so that's why they're sort of decorated.
Yeah, so for the data set that you've used so far, you've used airplane that is moving and going through space, but there are, well, wind or currents, they also move eddies and small-scale waves with them. So could you apply the same to a data set that is observed at one fixed point, assuming that there's a sufficiently constant current or flow?
Yeah, that's a very interesting suggestion. In fact, I thought one of the ways of using this is simply using turbulence or pipe data. I mean, stuff where you have a fixed observation location and the flow rushes past, like in the classical pipe experiments or something. In fact, I mean, the theory assumes that the measurement is taken instantaneously, which is not bad for the flight, for the airplane, which travels at Mach 0.8 or something. For the ship track measurement, it's actually a little bit embarrassing because the ship does not move at infinite speed. And if the track is like 500 kilometers long or something, it did take it some time to take the sample. So there might also be issues to do with that the pattern, the wave pattern at least evolves as you're taking the measurement, some kind of effect like that. But yeah, you could, if you have a sufficiently strong current, you could sort of do a Taylor hypothesis and just say, well, it's washing past, and I'm just getting the data out of that one. Yeah.
So thanks a lot, Oliver, for this very nice talk.
Thank you.
So we will have 5-minute break.